Let's learn about derivatives of and integrals of vector functions, but before I do that, I want to bring in something that I didn't bring in the last video, and I think it's kind of cool. It's this media that is from the book, and it shows you how a vector function is created using the, uh, the vectors. You see how it works. It's animating it. So what the curve is 6 minus t, and then this business here. And if you want, you can move it around and you can see what it looks like. That. Okay. There's another curve here, curve 2. Let's animate that. So if you look, see it's going around. It's tracing out the curves. This vector function, it's a vector function. R is x, y, and z. And if you look, it's a spiral. So spiral is going to be, or a helix if you want, is going to be a very common space curve that we're going to use in this class. Essentially what's happening is in the xy plane, you have a circle, and as the circle is being made, instead of making a circle like this, instead of doing that, what happens is as t is increasing, z is increasing. So you start drawing your circle, it starts at 1, 0, 0. And as your t increases, your circle increases like this. So you get this spiral effect. All right. So the helix is going to come up over and over and over. So it's good that you know it. Notice that if you look straight down on the z-axis, you get cosine squared plus sine squared is 1. You get the circle. In other words, you get x squared plus y squared equals 1. X is cosine and y is sine. And so that's how you get the 1. All right, so moving on, we can look at another curve. This is an interesting one. Let's animate this. So this curve is traced out by this vector function. Now you can't really tell what it looks like. Now see what's happening if you look at the bottom. We're going through values of pi. It retraced itself many times, so I think it's 2 pi. It's enough. Let's see how it goes. At 2 pi, we are done, and then it retraces itself. So let me pause it since it's retracing itself. And what it really looks like is this. If you look down from the z-axis, apparently you have parabolas here. This would be a good test problem to show that these are just looks like parabolas, and then looks like this looking down. I think that's the x-axis. Yeah, that's the x-axis looking down into the x-axis. So if you're standing on the x-axis, that's what it looks like. Okay, so that's that. I actually want to bring another one in here that shows it really well. Also, we were doing this as well. This is the curve sine t, cosine t, and then sine squared t. So if you look, x squared plus y squared is 1. Sine squared plus cosine squared is 1. So if I click on that, that is a cylinder, right? This is a cylinder. So this red curve is the space curve xyz. So if I click on that, that gives you that cylinder, right? That gives you that cylinder. So the curve lies on the cylinder because it satisfies this equation. If it satisfies the equation of the cylinder, it'll lie on that cylinder. All right, so let me get rid of that. Z equals x squared. So if you look, z is x squared. X is sine t and z is sine squared. So z is x squared. So it'll lie on this parabolic cylinder. Sure enough, it does. Okay. And then z is 1 minus y squared. Well, that's an upside down parabola. Z is 1 minus y squared. 1 minus sine squared is cosine squared, yes. So let's look at that. It's an upside down parabola. So there you have it. You can do this with other curves as well. Let's take out that one. Here's a curve like this. It looks like there's cosine going on. So you can see that that is just the intersection of 3 different surfaces. All right. So I thought that was pretty cool, and I thought I'd show you that that's in the tech media. So now let's look at derivatives, integrals of vector functions. I'm not going to go into necessarily why this is all true. I'm not going to go into the theory, but what I will say is this. If you have a vector function and that traces out a space curve like this, okay, then at any point, so we have r of t, then r prime of t, this is the tangent vector. Tangent vector. So, and that's what's going on here. This is the red vector is the tangent vector. Going in the direction that the curve is being traced out, r prime. All of this here comes from your Cal 1. And remember, f prime of x is limit as h goes to 0 of f of x plus h minus f of x all over h. And that looks like this too. You look at that in the book. All right, now the unit tangent vector, this is a really important vector. This is just the same vector up here, but we have just looked at the unit vector in the same direction of r prime of t. So you just take r prime and divide by its length. That gives you your unit tangent vector. Now, you can, if the individual terms of r of t are all differentiable, then r prime of t is just the derivative of each. All right, so then I would assume that you would know how to find the derivative of r of t, given that it's this. You just take the derivatives and then find the unit tangent vector where t is 0. Well, you just take well, actually, let's do this. It's not a bad idea to at least try it. So then r prime of t will be, I'm going to draw it with the brackets instead of the ijk. So this is 3t squared, and then we use a product rule here, e to the negative t minus t e to the negative t, and then 2 cosine of 2t, like that. Now r prime of 0 is 0, e to the 0 is 1, this turns out to be 0, and then 0, cosine of 0 is 1, so this is 2. So that's r prime of 0. R prime of 0, the length of that, is the square root of 0 squared plus 1 squared plus 2 squared, which is the square root of 5. So what they want is the unit tangent vector at the point where t is 0. We plugged in 0. So the unit tangent vector would be this one over this one. So it would be 1 over root 5, 0, 1, and 2, like that. All right, so what do we have next? For the curve, r prime sketch the position vector r and the tangent vector r prime of 1. Yeah, this is a good problem. This is a really good problem. I'd probably give this on a test. In fact, I've given this on tests before. So let's try that one out. Let me erase some of this. And let's do this problem. So you have r, so rt is t to the 1/2. I'm doing t to the 1/2 because I know I have to take the derivative, and then 2 minus t. Now r prime of t is 1/2 t to the negative 1/2, comma negative 1. And now r prime of 1 that would be 1/2 comma -1. All right, so let's see, r of 1, let's do r of 1 now, that they want us to do r of 1. So I'm going to take this one and do r of 1. So this is just 1 comma 1. So in green, we have this one, which is here. R of 1 is 1, 1. And now the unit tangent vector is 1/2 -1. So what I'm going to do is I'm going to go to that point on the graph, and I'm going to draw the vector 1/2 -1. Okay, so 1/2 -1, if you were to draw it without any reference, you go out 1/2 and you go down -1. That would be this vector here. Probably not to scale. So it's a vector that looks like this, something like that. And that's what they've drawn here in purple. That's that one right there. Okay, and that's how you do it. So you have your position vector in green here, and then you have your tangent vector moving down because you count that right there. Okay, so now it says these are good problems too. Sketch the plane curve of the given vector equation. Let's try number 7. So 7 is 4 sine minus 2 cosine, and t is 3 pi over 4. So let me pull that over. Number 7 is r of t. I hate the ijk stuff. It just gets in the way. So 4 sine t, -2 cosine t, and then at t is 3 pi over 4 is where we're going to find the unit tangent vector. So we're going to sketch this plane curve. So this is x and this is y. So x is 4 sine t, and y is -2 cosine t. So if we divide by 4 on x, we get sine t. And if we divide by -2, we get cosine t. So it looks like if we square both sides, we get x squared over 16 plus y squared over 4 is 1. So this is an ellipse, which is more in the x direction. So we get something like this. So let me draw that in a different color, black. Where right here is 4, and here is -4, and then up here, when the y direction is 2, and down here is -2. All right, so that's the ellipse. So 7 says, so we sketched it. And now find r prime of t. Well, that's not hard, we just find the derivative of it. So now r prime of t is 4 cosine t, and then 2 sine t, like that. And then at 3 pi over 4, we get 3 pi over 4 is -√2 over 2. Please know that without a calculator. And then sine of 3 pi over 4 is √2 over 2. Know that without a calculator. So this gives you -2√2, comma, √2. All right. So now r of 3 pi over 4, let's find out what that is, because they're asking us to sketch the position vector and the tangent vector. Okay, so r of 3 pi over 4, let's draw that in red. Let's see, where's r? Here's r. R of 3 pi over 4 will be 4 times √2 over 2, comma, -2 times √2 over 2, that's negative. So this gives me 2√2, and then -√2. Okay, at 3 pi over 4, we go over 2 root 2 and down root 2. So what this tells me is that this ellipse is traced out over 2 pi, maybe twice. Let's see. No, this is positive here. I had a negative. This is a positive. Those cancel. So now it makes more sense to me. Okay. So r of t, r 3 pi over 4, is 2 root 2, comma root 2. So we're going to go out a little more. Then we go up. So there's the position vector. Now r prime of t, what color did we have that? We had that in black. So r prime of t at 3 pi over 4 was negative 2 root 2. Is that right? Yeah, and then root 2. So from that point, I'm going to go back and up. Let's see something. Yeah, that makes sense. We're going to go back and up, so it's going to look like this. So this is r prime, and this is at 3 pi over 4. Now let's see what is going on here. I think the ellipse is going in a, excuse me, oh, go back. In a, don't worry about this one, it's going this direction, in a clockwise direction. And it's true because you have sine first for the function. See, for the function, it's sine first, and then cosine. When cosine comes first, then it goes counterclockwise. All right, so there you have it. That the derivative told me that it's just one more confirmation that it's going in the clockwise direction. All right, so let's move on. All right, so it says find. I'll let you do this one. That's in the book. Find the unit tangent vector at the point given the parameter. So you just take the derivative and you plug it in. Let's try one of these. How about number 18 looks rough. So number 18, here we go. So what I'm going to do is I'm going to cut this and paste it. Okay, so here we are. So we're going to do r prime of t is the derivative of inverse tangent is 1 over 1 plus t squared. And then the derivative of this one is 2 times 2 e to the 2t. And the derivative of the last one is the product rule, so that's 8 e to the t plus 8t e to the t. Now r prime of 0 is going to be 1, 4, because e to the 0 is 1. And then comma, this guy will make that part 0, so this is 8. And so the unit tangent vector at 0 is going to be, oh, now we need to find the length of this. And so that's the square root of 1 plus 16 plus 64, which is square root of, goodness, does that equal 81? I think it does. Yep, so that's 9. So the t at 0 is 1 over 9 times 148, which is 1/9, 4/9, 8/9. And there you have it. So what's coming up? Let's see if I can do some more problems for you. Let's see here. Yeah, this. So I think you can do some of these problems here. 34, I think that's in the examples. Differentiation rules. Now this is important because you need to understand what the difference between these things are. U and V are vector functions, C is a scalar, and F is a real valued function. So when they say F is a real valued function, that means that it's like F of t is some kind of number, or it's at least a polynomial, okay? So it could be t squared plus t, or it could be F of t is sine of t. It's a function that when you plug in a number, you get a number out. These vector functions are when you plug in a number, you get a vector function out. So when you have here the derivative, the first one, when you have the derivative of a vector function plus a vector function, it's the sum of the derivatives. If C is a constant, if it's a scalar, you can pull it out. It's not a problem. It's this one. Now, here is a vector function multiplied by a real value function. So an example of this might be t squared times sine t cosine t. So to take the derivative of this, you would just use the product rule. Basically, it's the product rule from Cal 1. F prime g plus fg prime. Now, if you look, the dot product is a product. So the dot product is going to be the product rule as well. Same with the cross product. Okay? And now the chain rule just works like it did before. So the chain rule, remember, was the derivative of g of f of u. Well, how was it? F of u of t. The derivative of this was f prime of u of t times u prime of t. That's what's going on here. So it's, well, okay, so I'm confusing you completely. This is from Cal 1, and this is from Cal 3. So it's just the derivative of the inside times the derivative of the outside. That's all it is. All right. And so integration, very similar. You just take the integral of all of them. Now, there's a complication in this that I want to show you, and that's number 41 and 42. Which one do I want to do? Let's try 41. So 41 gives you the derivative, and it wants you to find r. So 41, r prime of t is 2t, comma, 3t squared, comma, square root of t. Let's write it as t to the 1/2, because we're going to have to integrate this. And then it says r of 1 is 1 comma 1. So when you do this, you take the integral of r prime of t dt, you're going to get t squared, t cubed, and then add 1, divide by it. So that's 2/3 t to the 3/2 power, plus a constant. Now, it says that, so the left-hand side, this is r of t. So it says r of 1 is 1, 1. So r of 1 is 1, 1. It's 1, 1, 0. They left off the k, so that's a 0k. See right here, it was 1 plus, there's I plus j plus 0k is really what's there. I was getting worried because there's a z component here, and there was no z component in the 1, 1. So r of 1 was 1, 1, 0, and that's equal to t squared, t cubed, and 2/3 t to the 3/2 power. So what this says, okay, plus c. So what this says is 1, so this c is basically c1, comma c2, comma c3. So it says 1 is equal to t squared plus c1. And this is at r of 1. So r of 1, make that a 1, so c1 equals 0. So what I did was I plugged in 1 for t. So I got this one here is here. So I got 1 equals t squared. I plugged in 1, I got 1. And then plus this c1 there. Now let's do it for the y component. So so this was x. So now y is 1 equals t cubed. This t cubed, we plug in 1, we get 1. 1 equals 1 plus c2. Well, that implies then that c2 is 0. And now let's check out the z component. Z is 0 equals 2/3 t to the 3/2 power. Plug in 0, you get 0 plus c3. So c3 is 0. So it looks like c is 0, 0, 0. I have to put a line over c over here. Okay, so then r prime is just, I'm sorry, r is just this right here, because the c's end up being 0. So this means then that r of t is t squared, t cubed, 2/3 t to the 3/2 power. You can leave it like that. There you have it. All right, so let's see what else is here. This is a good problem to do on a test. See if you can do that one. It's a nice little problem there. All right, and that's it. That's vector functions and their derivatives.